I'm sure that won't present any problems. They have room right here. Okay, now, what I've been told reliably, you're not on your phone, are you?
No.
What? Don't make me treat you like Emma. I've been reliably told by your math teachers that logarithms are your favorite thing in the entire world.
I'm just confused about this.
And
This isn't fair.
number one, I'm going to start off saying logarithms, the way we're going to do them, are the easiest thing you're going to do. If you haven't ever done them before, they're fine. We only do log base 10. We treat them with the contempt they deserve. They're a servant to science. We don't have to do anything fancy with them. And you should be able to look at it and just get a reasonable answer as to what it is. If you want to get out your calculators, you can, but I'm going to ask you to put them away in a second.
What is hydronium?
What? Oh, sorry. Anybody not done with this?
No, but what is?
Oh, that's Atrio Plus. Its name is hydronium.
Oh, okay.
Yeah, that's it. What is the log base 10 of 10? Yeah. What is the log base 10 of 100? 2. What is the log base 10 of 0.1? Negative 1. For anybody who's going, how do they get these numbers? Can someone explain where they're getting these numbers?
It's the what power? Exponent?
It's the exponent of what?
Of base to get to the like number that's not, I don't know.
I know what you mean by base, except if you say it in chemistry class, it sounds a little weird. If you took this number into scientific notation, what would it be? 1.0 times 10 to the negative 1. If you took this number, put it in scientific notation, it would be 1.0 times 10 to the 2. If you took that number, put it in scientific notation, it would be 1.0 times 10 to the 1. So the logarithm is just those numbers. That's it. So if I say log, Marcus, log base 10 of 1.0 times 10 to the minus 3 is negative 3. This is not hard. If I tell you that I want to know the log of 5.0 times 10 to the minus 2, Portia, what is that?
I'm not in math.
No.
Oh.
What is the log? Log base 10 of 10 was 1. Log base of 100, 100's got 2 zeros, so that was 2. That is zeros the other way, so it's 10 to the minus 1, that's minus 1. 1.0 times 10 to the minus 3, the log of that is minus 3. So if you take the log of that, you should get roughly minus 2. Okay. Now, should you plug it into your calculator to get exactly what it is? Yes. But if you get an answer, I would expect you to go, I don't know what, 5 times 10 to the minus 2, you're probably going to get what? Minus 8, 7, 4, something.
Negative 1.3.
Negative 1.3. Not 2. Is it close to minus 2? Yeah.
It doesn't really.
Yeah, it's close. Because what I'm looking for is when you get an answer, you don't give me 18 or 1.0 times 10 to the minus 20, as I've seen in one case. If you're taking the log of something, you should know instantly, oh, I must have pressed the wrong button, because it's going to be near minus 2. Minus 1.3 is close. If you're an astronomer, what's the value of pi? No, it's 10. Makes all the calculations easier. They deal with numbers so big,
That's not it then.
pi is equal to 10. Because it doesn't matter.
So why do we need them?
Well, if you're doing precise calculations, but if you're working with science, you're working with an error. As long as your assumptions are less than your error, it doesn't matter. That's, you did the 2 plus 2 equals 5 last year in chemistry 11.
No.
This is a measured number. You measured that. What's the error?
0.
No, from last year, if you measure something, like if I measured 2.01, what's the error? 2.01 plus or minus 0.01. It's always plus or minus 1 in the last digit. You didn't learn that? There's more sophisticated ways of doing error, but if you measure something, like with a ruler, you always, you learned about that's a certain value, and this is a guess. Did you learn about the guess? Yeah, so that's the guess. The error's in the guess, and it's always plus or minus a digit in the guess. So if someone gives you a measured value of 2, then it's 2 plus or minus 1. So 2 plus or minus 1 plus 2 plus or minus 1. Sorry, bracket's wrong there. Because that's our error, can equal anything from 2 to 6. 2 plus 2 does equal 5. For very large values of 2, those might be big 2's, or they might be little 2's. We don't know. Because the error is plus or minus 1. That error is huge. You can make all sorts of assumptions when your error is huge. Did a physics lab once, and there was a value we didn't have. We couldn't do the problem without the value. We asked the professor, and we said, we don't have this. We have one of those, there's too many unknowns for the equation. And he says, oh, just use E. We're like, is it E? And he's like, no. But it's a small number like E. So it'll work. And it worked. You could then check the results, and it was like, yeah. If you're dealing with error, you can get away with lots of stuff. Identifying Bronson-Lowry acids and bases. So, logarithms. Oh, maybe I should do it the other way too. Log, roughly, of, I don't know, 5.6 times 10 to the minus 10 is equal to what? Minus 10. Minus 10. Excellent.
So that's the beginning number, even though
What is the anti-log of 5?
negative.
Negative 5?
I don't know.
You're actually more right than you know. Yeah.
Negative 10. I'm more right. Oh no. 0.6. It's an 0.5. 2.5. 10.0.
Just do the opposite of what you
1
did.
times
You
10
took
to the
this
5.
and you put it there. So we take this and you go 1.0 times 10 to the 5. Right? Yeah. The reason, and if I say, what is the anti-log of, I don't know, minus 3?
1.0 times
1.0 times 10 to the minus 3. The anti-log is a fancy way of saying 10 to the x. You will have a button on your calculator that can calculate that. The reason I'm introducing logs now is because pH is equal to the negative log of the concentration of H3O+. And the reason you were righter than you knew is because we put a negative sign in that. So if the concentration of H3O+ is equal to, it is 0.010 molar. What is the pH of that solution?
negative 2.
So close.
0.
I put a negative sign in the front.
Oh,
2. By putting a negative sign in the front, we got positive values because we don't want to work with negative values, and that's why the pH scale, the acids get stronger as you go down the scale, because we put a negative sign. If we didn't do that, we'd be working with negative numbers, and people hate that, so the person who invented it just put a negative sign in. We'll do that later, but little review of logarithms. You're going to need it in a little bit. It's not hard. You can just look at it and know. And we're not going to do like natural log or any nonsense stuff that isn't useful. I keep expecting a math teacher to walk in the room and strike me dead. Identifying Bronson-Lowry acids and bases. So this proton donor acceptor, and you do need to know the difference by name. So Bronson-Lowry is the new one. The old one, go back one more, was called Arrhenius. So if you didn't highlight that at the time, you do need to know the difference. And the way I remember it is it's in alphabetical order. Arrhenius comes before Bronson-Lowry. Now hydrogen's an electropositive atom, a naked atom. So what kind of atom does it want to get with? A clothed one, which would make it electro negative. Remind me, what does electronegative mean? Yeah, Mark. Evan volunteered.
Like, just like the amount. Is it the amount of energy that you take an electron? No.
To be honest, it's almost close enough. That's ionization energy. Yeah.
Is it the amount it accepts others or something? I forget.
That's close too, because others, it is a shared electron.
Its likeliness to accept others.
No, that's a reverse ionization energy. So ionization energy is the energy required to pull off an electron from a free atom, a free electron from an atom. And there's a reverse of ionization where you can force an atom to accept an electron.
Is it how strong
The only difference between electronegativity and ionization energy is the electron is shared in a bond. So how well does it hang on to an electron in a bond? And oxygen pulls on them really hard. Karis, question?
She was complimenting your
Oh.
teaching.
I feel confused. Yeah.
Does that apply to almost all acids?
Does what? Does what? That applies to the universe. I mean, electronegativity is just a property of atoms. So if you want a proton donor, if you want something to give up the hydrogen, and it's very electropositive, place it with something that's really electronegative. If it's really electronegative, then it's going to pull on the electrons even harder. And what will that do to the bond? It'll break the bond. The hydrogen doesn't really want the electrons. It's trying to throw its clothes off all the time. And the other thing wants to get the clothes. If you put it in water, then the water will just be the tipping point that throws it over the edge. In terms of what is a proton? Proton, nucleus. Jesus. There we go. Electron. What has to happen for that to become a proton? just a proton.
The
The electron has to go away. So the electron goes away. And we end up with our nucleus. Is this the scale in terms of time, size of the orbital versus size of the nucleus?
No.
No. The proton and the nucleus is very, very tiny. The orbital is very, very huge. So this is very, very large. Yes.
Does this apply to covalent and ionic bonds?
You were too quiet. And Marcus is talking.
Like, does it apply to both covalent and ionic? Because don't they
Oh, I mean, yes, in a way. A covalent bond is when they're sharing electrons. And a polar covalent bond is when one side is so electronegative it actually pulls more of the electrons towards it. And an ionic bond is when that has happened to such an extreme level that one side has all the electrons, and now they're attracted by charge instead of shared electrons.
So, if it, like, in covalent bond, it's never, like, fully...
It's never fully broken. Yeah. So that's the only difference. They actually still attracted by their shared electrons.
In ionic, it can be fully broken.
In the ionic is fully broken. And they're only attracted by charge. It's an electrostatic attraction. And this one is very, very small. Very small. It has then a concentrated charge. And it's going to be very, very attracted to any negative charges. Concentration can do a lot of things with force. If you take a very small amount of force and concentrate it into a small area, you can create a lot of damage. If you take a lot of force and expand it over a large area, you can dissipate that force and it won't do very much damage at all. I attended a housewarming with a couple who had just put in very nice hardwood floors, and a lady came and the end of her high heel had popped off, and she was wearing very narrow spiked heels, and she punctured holes all the way in her hardwood floor because her weight down to essentially a needle point was strong enough to break through wood. And another time I had to take a D8 cat, not a like kitty cat, but like Caterpillar, big yellow machine, across a road, and we would have had a huge fine if we had ripped up the road at all. So we just took the tracks, and they have special tracks. You just put really wide tracks on it, and then we came up with a system by we made them even wider with wood so that we could get it quite wide, and then it went right over the entire thing. You can actually get specialized tires for cars for specific events in which the car can drive over you. It dissipates the force so much that you can't even feel the weight of the car. But if you concentrate it down to a very, very fine point, that's a fair amount of weight, and even small amounts of weight, if concentrated to a small point, can do a lot of damage. One of the reasons why an acid is so reactive is not just that it has a +1 charge. Everything has a +1 charge. Tons of things have a +1 charge. Lithium has a +1 charge. But it is a single proton, the tiniest object that you can interact with in the universe, and it has a full +1 charge. And that very tiny object with a full charge is concentrated enough to now do a lot of damage. Or, another way of saying it, react. It's going to go looking for something to react with. From Lewis dot diagrams, what are those?
Electrons?
The There are electrons. What do we call them?
Valence electrons?
They would have to be valence electrons. Yep. Hi-ho, silver away. No, that meant nothing. Lone pairs.
Oh yeah.
Wait, what did you say before you said lone pairs?
Hi-ho, silver away. That's a reference that precedes even my time, because that would be the Lone Ranger.
What does it mean?
He was, I don't know, a TV series. And that was one of his catchphrases. But I think the show only existed in black and white. I saw reruns of it when I was like 5. It's very old. They tried to make it come back with a movie. That flopped badly. Ooh. Hold on. Where is he? Start looking at it, I think. Oh, your data table. Turn to page 6.
Oh yeah. Is that new? So it actually has it. Yeah, he's pissing.
Okay, page 6. I'm not going to talk too much about this because we haven't done Ka yet, but you can see it's listed in strength. Which is the stronger acid, Hi or HF? Got to find HF and Hi on your data table. They'll be on the left-hand side under acid.
HI is very large.
HI is very large. The ones that are shaded, they are defined as strong acids. There are only 6 here. Perchloric, hydroiodic, hydrobromic, hydrochloric, nitric, and sulfuric. Hydroiodic acid is a little bit below that. Where is it?
It was in.
Sorry, HF, not hydroiodic. HF is way down here. Whereas hydrochloric, HI, HCl. Why not HF? In terms of some of your trends from last year, what is the difference between iodine and fluorine? It is more electronegative? So it should attract it even more. And let's rotate that. What? I don't want you to prepare it for reading. The other way. There we go. That's more electronegative. What else? Compared to down here.
More reactive.
It's more reactive. Those both depend on something else, though. It is smaller. The reactivity and other things often depend on atomic size. Fluorine is much smaller than iodine, and that makes it weaker as an acid. If we have H, now I, so HI, because I is so big. And then we have HF. They fundamentally look the same in terms of lone pairs. Bigger atom,
8.
smaller atom.
And the line is 2. I don't know. Just you see 2 on each. I don't know. I know it's right. I don't know why.
Now, the attraction we're looking at, because remember, we're not looking at H+, we are looking at H3O+. So hydrogen needs to be attracted to there. Electrostatic attraction. So we have HI, and pretend they're the same distance. I don't want to rotate it up here. But the only difference is who it's on. Which hydrogen is more likely to leave its partner?
The H.
HI. Why?
It's farther away.
It's farther away. Long distance relationships never work. You know, HI dated in high school, and then they went to university, different universities, and hydrogen, there's some other people a lot closer, a lot more attractive. Going to the same classes they were there, right there in class. Studies of future relationships show that geography is the single most important factor of whether or not you're going to get to know someone and marry them. To the point that your distance by dorm mattered. As in, if you were 2 doors closer versus 5 doors farther away, you were more likely to enter a permanent relationship. Or at least in one particular study. The Hope-Rogers experiment resulted in more children and marriages than any other Brentwood experiment we've ever done. Hope-Rogers? There was a time when Hope House did not exist and we only had 3 female houses. And they needed to add another house, so they cut Rogers' house in half, put Rogers on one side and Hope on the other, and they shared a common room. And then a lot of them got married. Weird.
We still have traditions from that.
Yeah, it was a huge deal. Privet got some of the Rogers rejects. Because when they cut it in half, not all the old Rogers students would fit in the new Rogers house. So they asked for volunteers to move from Privet, and so we got a bunch of the ex-Rogers guys. And that's why there's now Privet students with Rogers legacy in Privet. And vice versa. Bigger atom, greater the bond length. Better proton donor. I did hear someone once suggest we should do that with all the houses. Because if they're interested in future donations, there'd be no faster way of creating a lot of new Brentonians. But nobody seemed to be really keen on that, so marketing stopped. So the size of the atom matters. If it's really large, it's just going to give up the hydrogen a lot more easily, larger distance. Less attraction. We don't go into why there's less attraction, but anybody in physics in this room? Anybody in physics 12?
Yeah.
What is the relationship between distance and attraction? Do you not do planetary laws in physics 12?
I don't know.
Gravitational laws?
I'm in AP, but I don't pay attention.
I'd like to hit you with this so hard.
I'm doing good.
Excellent. In English?
Not as good in English.
Because you would say you're doing well.
Oh.
If you're doing good, you're feeding the poor, and giving money to the sick. Okay, what do we call a proton acceptor? What's the traditional name? Something you should never drop. The base. A proton reminder, proton acceptors, these are bases. Bomb. In today's political environment, please don't make jokes about dropping bombs. The International Consortium of physicists put the doomsday clock at 18 seconds. 2 weeks ago, I think. It's the closest it's ever been. It's their estimation how close we are to total world annihilation.
18 seconds.
18 seconds. The last time we were really close, I think, was during the Cuban Missile Crisis.
Doesn't make any sense, 18 seconds.
It's their indication of how far away we could be at any particular moment. They're the ones that are also charged with going around the world and inspecting all the nuclear plants, making sure people don't have nuclear weapons. They added in climate change to their list of dangers and a bunch of other things as more scientists have joined. It's just one group of people's opinion who have advanced degrees and study this sort of thing. Be safe up there. Okay, our classic one, NH3. If I was, draw the Lewis dot diagram of ammonia as fast as you can.
No, you're wrong.
10 seconds. 9 seconds.
Oh, yeah, you got it.
8,
That's all.
7, 6, 5, 4, 3, 2, 1. Grab a partner and write what you have on the board as fast as you can. Go. Lewis dot diagram. Lewis. Go. Hi. You also look like you needed to walk. Marcus, grab two partners. Go on the partner. Oh, no, you didn't move.
I
No. Grab someone. But you have to walk. You have to walk up. The point was to make your legs move, so blood started flowing. Declan's actually falling asleep. Your eyes were closing.
That's
I'm not trying. It looked like it to me. What? No. Gentle. Look, don't touch. You're grade 12. Drop it. Grade 4. Yeah. Okay, a lot of good. Oh, perfect. We're good. We know how to do that. Am I going to make you draw Lewis dot diagrams? No. Are you supposed to know how? Yes. Would it help you? Probably. Just don't forget about the lone pairs. If you just remember that nitrogen often has a lone pair, that probably does you for about 90% of it. And oxygen often has 2. That is.
Why does nitrogen have more pairs?
It has 5 electrons.
Does it nitrogen not have?
Oh, yeah.
How many valence electrons does nitrogen have? Nope. Not 4. 5. So, oops. Do it properly. N, 1, 2, 3, 4, 5. Oxygen, how many electrons?
8. Oh, 2.
Valence.
2.
6.
No.
6.
6.
6.
1, 2, 3, 4, 5, 6. As you may remember or may not, these are the ones that want to bond.
Aren't each of the lines 2?
So these want to find a partner. That's why oxygen always has 2, nitrogen only has 1. Can nitrogen use that to bond? Sure. That's where H plus comes in. So H plus goes there and just globs onto it. Did H plus provide anything to this relationship? No. It just came and used what's already there. It's a mooch. It's sleeping on the couch and eating your food.
Wait, I thought the lines where 2 electrons.
They are. I was using that for emphasis, not to show it on. But this is where it was, right? But these are lone electrons, right? So we put chlorine here.
But okay,
Bond.
wait, what?
I'm not reteaching Lewis diagrams, but I will happily do it maybe at the break. Because all I really want to show let's make you smaller. That's infinite clone you. So we have ammonia and we have, I won't make you get up, but draw the Lewis dot diagram of HCl.
What?
HCl. 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 How many lone pairs does hydrogen have? None. Trick question. How many does chlorine have? Lone pairs.
3. Oh, no, I had 6.
Those. Oh yeah. You had it. You're just saying it wrong.
No,
Don't do
this is
that.
confusing me. You're confusing. Yeah, it doesn't make sense. Cause like, what I've learned is you like.
Isn't there 8 electrons attached to that
Yeah, I
chlorine?
thought there was 8.
Or no?
But you're.
Am I
Okay, never mind.
Well, does a central atom have an octet? Yes.
Okay, yeah, what?
You're talking about the octet rule?
I don't remember.
The octet rule is the central atom has to have 8 electrons. It doesn't have to have 8 bonds.
That's what.
8 electrons and bonds. But the lone pair provides the rest of the octet. Okay. Elena, what do you do? You have a concussion, you're allowed to be on devices. And be on your phone again. You're helping your what? Okay, that's fair enough. Okay. This chlorine, like hydrogen iodide, is really big compared to fluorine. It's going to take all these electrons away and kick hydrogen off. What is hydrogen going to be attracted to on the ammonia? The lone pairs. The ammonia has these really attractive lone pairs. And hydrogen comes over and says, hey, how are you doing? Does hydrogen take the electrons with it? Does hydrogen take the electrons with it? No, this is a sad case. Chlorine is very electronegative. It took all of hydrogen's stuff and kicked him or her out of the house. Like my poor brother. He was engaged to be married. They were going to get married in 3 days. He came home and everything from his house was gone. Like everything. Like the dishwasher was disconnected and taken out of the house. The light bulbs were unscrewed. The panels off of the wall for the switches, gone. She took everything. It was his house. He still doesn't know why. They were going to get married in 3 days. They didn't have a fight, as far as I know anyway. And we don't know. We just
never
learned-
saw her
Oh, never saw her again. I mean, she lives in the same small town. He moved, but it was strange. Yeah. Although, when we met her for the first time, we knew she was crazy. So she had a 3-ring binder. You know the big D rings that are like that big? All it was wedding plans that she'd been making since she was 5 years old. So 3 days before the wedding, I think she realized that her whole binder would be gone and she'd have no other purpose in life, and that just panicked her. And, and maybe she realized, what? No, you don't know my brother, so. Although if you watch some YouTube videos. No, but he's in some because he used to do show stuff where if your muscles.
Is he a body?
He was at one time.
Can we see highlights?
What's his name?
No, I know. I'm not gonna reveal.
What's his name?
Then we don't believe.
don't believe. There's like 2 videos out there. I guarantee you're not gonna find it. If you find it, I'll be impressed.
What's his name? You have to know his name.
No, I don't. You have enough clues. You know my name.
Mr. Bell, if we find it, will you hire our grade for us?
No. I'll give you a treat.
Higher grade.
Not a higher grade. Okay. So, what are the products?
Sienna, she's already searching for it.
Is his name
Search him.
Eli?
What?
Is his name Eli?
Morgan Neufeld. Wait, what?
No, and not
No.
Eli either. Eli's,
It's not Eli.
Sienna,
Very
search for
Jewish.
bodybuilder Neufeld.
I guess
That's what
Neufeld.
I did.
Yeah, maybe. But no.
What
Victoria?
Bodybuild?
Does anyone know what it's
Hugo?
I'm just going to keep going with the lesson because I've realized my mistake.
Do you have LinkedIn?
Ambrose?
Do I have
Is it
LinkedIn?
Ambrose?
I made one LinkedIn because I needed to message
Yeah, we
Mr.
see
Lee,
it right now.
and he was on LinkedIn. So I thought, oh, I'll make a LinkedIn profile just so I can message him and not use it. I have gotten more spammed from that thing than anything else.
Where'd you go to school?
2008.
Where'd you go to school?
Okay,
You went to UVic? Okay, so this is you.
please put away your devices for now.
Let me see. Oh my god. Did you find it?
No, it's not Eli.
Is it Ambrose?
It's not
Is
Ambrose.
it Hugo?
It's not Hugo.
Wait, can
Is
you
that like
just
a
show
common
us the
name?
picture?
What's the name?
Yeah?
Mark.
At one point in time, it was a common name.
Does he look like you?
No, I will confirm a name only if you find an example. I'm not going to randomly confirm names. That's too easy.
Jack.
Yeah. I have an Uncle Jack,
Isaac.
but my Uncle Jack was mayor of the township of Langley.
Is it
Is that where
Brandon?
you're from?
Langley? No, God no.
Is it Brandon?
Oh, God, if I had a Brandon in the family, I'd have to like shoot myself. Can you imagine having a Brandon? It'd be terrible. I apologize to anybody whose middle name is Brandon or anybody listening named Brandon. I just realized this is all being recorded.
Mr. Neufeld.
No, that's me. That's not my brother, that's me.
Someone look up Neufeld and Dimitri.
That's my friend too.
His name's Ro.
Lewis dye diagrams for hydroxide and CO3, 2 minus.
Newfoundland.
Is that
What? You're locked in.
Oh my god, he had a goatee.
Oh, what?
You found it.
No, we found young dude.
If you,
It's a picture you tagged Privet throws down gauntlet for Haiti fundraising.
You look great.
oh yeah, that was way back when. We didn't throw us down gauntlet. When the Haiti disaster,
According to Google.
when the Haiti disaster happened, myself and the boys of Privet just started fundraising right away, and then a bunch of other houses joined in, and we just raised a lot of money for the. That was when we had the tidal wave. That was really bad. Okay.
Fuck you.
I want to do in a Star Trek uniform.
Mr. Neufeld.
Is his name
No, hey, you're saying that with some levity. How do you know I got married in my Star Trek uniform?
Really?
Yes,
Mr.
of
Neufeld.
course. It was a uniform.
Mr. When were you born?
Pardon?
When were you born?
When was I born?
Yes.
Why do you want to know?
This is very important.
1971.
Thank you.
You can now calculate my age. Okay, I'm going to ask you to grab a partner and these 2 Lewis dot diagrams, because I don't think I'm going to rip you away from your devices otherwise. Those 2 on the board. You've got 15 seconds. Come on. Focus.
Wait.
I love that one.
I have my head.
It's not on my hair.
I have my brain.
Picture something I would.
Oh wait.
Now I know. You need to go into your kids' Instagram and see what they're following.
No, Gordon's a famous Neufeld, but not my Neufeld.
He's not on my list. Don't try. That's why I said up here.
Gordon Neufeld is like a child psychologist or something.
He's also dad.
He might be dead, yes.
How old is he?
I'm the eldest.
So he's younger
Is it
than you.
Mason?
And you were 71? Born in 71?
Yeah.
Most common.
Is his name Mason?
No.
Are we getting closer?
Is your brother older or younger?
I am the eldest in my family.
So he's born
I
after
was the one in charge.
1970.
Yeah, we're all good.
Okay, once you've got yours,
I don't know if that's right.
if you have single bonds for your carbonate, I believe you are incorrect.
Was it Herman?
You are not following.
Is it Herman?
No, God. That's like great grandpa's level of Mennonite. Oh my God, you broke the octet rule.
I don't remember. Oh, this is not. Yeah.
Maybe only one.
Okay, everybody seems to have hydroxide.
Oh, Marcus, I remember. Only.
I don't remember it.
Wait.
Oh, yeah, only one. I don't know.
I feel like that's.
And then, yeah, it's something.
That makes sense.
Oh, you add up.
Oh, does that say OH?
Huh? I'm gonna try to do this.
Once you get to this point, you've used up every bond is 2 electrons. You have a total of 24 from the charge, the oxygens, and the carbon. You have 18 electrons left. Where do you put the electrons? Around the O's. And so how many do they need to complete their octet?
4. 6 more.
6. So give each 6. How many electrons did I add? 18. So I'm done. I have no more electrons. That's why you need a, what kind of bond? No bond, because does carbon have an octet?
Oh, no.
No. So that's why you just take one of the lone pairs, give it a double bond. There you go.
Wait, how did you jump into
Carbon has 4 valence. 3 oxygens is 18. And the negative charge means there's 2 extra. Does that make sense?
and then why do you minus 6?
Oh, because I put in a central atom, put the oxygens around, and then bond them. Every bond is 2 electrons.
How was 3 oxygen 18?
What are you doing?
Who said that? How many valence electrons does oxygen have? That's all it was. You don't have to know Lewis diagrams. I'm not going to quiz you on Lewis diagrams, but it is helpful. And honestly, if you just remember that oxygen has lone pairs on a lot of them, you'll probably get away with a lot. This is an incredibly good base. As we know, it attracts hydrogen because not only does it have a ton of lone pairs, it also has a full negative charge, and so hydrogen's going to love that. But this is also a base, so that's not ammonia, and it's not hydroxide, but CO3 minus 2, hydrogen with no charge is going to be highly attracted to all that negative charge. So you'll end up with CO3 minus 2 plus, and what is the new formula for hydrogen?
H3O.
H3O plus.
Yeah.
I'm going to have to warn my brother. If any of his view count starts going up, you should let me know. Goes to, now it gives off 1, so we get H, CO3. What should the charge be? Well, if we take H off of here, what are we left with? What's H3O plus minus H plus? H2O. So if this is now H2O, must the charge be here?
Wait, what? Plus?
It started off as -2,
Minus 1.
-1. We added a +1. The other way to look at charges, what's the total charge on that side? -1. The total charge on this side must also be -1. In addition to balancing of atoms, there's a balance of charge. And you can also double check your balance of charge if you have it correct. Later on when we do redox balancing, students will come to me and say everything's balanced. And yes, your atoms are all balanced. But that's when we start getting really picky about are your charges all balanced. We've never given you those problems before.
Wait, H2O doesn't have a charge?
No, it's just water.
What
It just has lots and lots of lone pair electrons.
Why is H3 have a charge?
Because it has H plus.
It's not.
In the same way that hydrogen joins here to make ammonia.
So how is it balanced?
How is it balanced? It is balanced. What's not balanced?
Not balanced. What's not balanced?
We got 3 hydrogens. We got 1 carbon, 1 carbon. We got 4 oxygens, 4 oxygens.
No, I mean the charges.
Oh, what's the total charge on this side? -1. What's the total charge on that side? -1. So a quick way to check, if you knew that that becomes H2O and you wanted to figure out what's that charge, that's another way of doing it. The other way of doing it is remembering, okay, what's happening here is that H plus is coming off of this, and so the charge and the hydrogen is moving. So we have to take away a plus and away a hydrogen, and add a H and add a plus. So these were both what makes a good proton acceptor. Have lots of lone pair electrons, that will attract them. Have a negative charge, that will also attract them. So, this is ethanol. Is this an electrolyte? Does this conduct electricity? No. This doesn't want to donate a proton, and here's where I explain why these things are not either acids or bases. This is ethanol, otherwise known as drinking alcohol, and carbon. Is carbon electropositive or electronegative? It's electroneutralish. Carbon's right in the middle. A reminder from last year, it's right in the middle. It can go +4, -4. It has twice the chance of a date on a Saturday night. It can do covalent bonding. It could theoretically do ionic bonding, although it often doesn't. It is the substrate for all of organic chemistry. And it's electroneutral. It's not very electronegative. It's not going to pull electrons very hard away from oxygen. It's also not very electropositive. It's not eager to give them up either.
So when it comes to like the bonding, would it change? Does it affect how we bond?
So what it means is that oxygen is not going to pull on that hard enough
Yeah.
to pop off and make hydroxide.
Okay.
It also means that this bond here, because hydrogen wants to keep its electrons, that transfers a little because it's keeping that fairly neutral. Oxygen is pulling in the electrons a little bit, that is polar, but it is oxygen is less electronegative than chlorine, and so it's not quite enough in this case to release the H plus. And now I'm focusing on this, and it will make more sense with the next one because there is a way that we can make carbon electronegative. So this is not usually an acid. And I have to say not usually, because chemists have figured out ways to force it by being really, really mean. This is an organic acid. This is an R group. If you make it, for example, CH3, C double bond O, OH, you have vinegar or acetic acid. So this could be anything, any amount of carbons. What this does is oxygen is electronegative, and this pulls different color I need there. Electronegative pulls electrons, and that actually pulls electrons away from the carbon. Carbon gets upset and pulls electrons from here. It's like they're taking my electrons, that's our little pairs on, and so it pulls more from here. Oxygen already electronegative, not putting up with that nonsense. What do you mean carbon's grabbing my stuff? I'm just going to steal more electrons from hydrogen. That's supposed to be an arrow. Electrons pulled from OH, and they're pulled this way. So the electrons go pulled there, and are pulled there. So that just creates an effect that makes it even more electronegative than it normally would. And this is why this is known as an organic acid, because then you get RC double bond O, O minus, plus H plus. Now, R, C double bond O, OH, and R, C double bond O, O minus. In a written form in your textbooks, exams, future notes, university, you will see it written as two O's in a row, meaning double bond O and O. And the reason for that is that is a shorthand back when we used typewriters and we didn't have software to properly draw in organic chemicals into a document. So they would just use that as shorthand. And because it is still so easy to do, it's still done. You'll still see that. So that's an organic acid. These two are interchangeable. The top is the real structure and the bottom is what you will often see in problems. Citric acid has one of those on it. Acetic acid has one of those on it. Formic acid, which is antbite, that poisons your optic nerve, which you make if you drink methanol, that then poisons the nerves in your body and puts you into a coma, has that. Oh.
Wait, not yet.
No. Next day, we're going to do conjugate acid-base pairs and equation writing. I am going to stop here. You have done a lot of theory today. Thank you, because I know theory is not necessarily, and structure is not necessarily the most interesting to sit and do. But I'm going to stop. I made it before the end of class, which is my goal. And then we're going to write some equations. Next, so Brunson-Lowry acid-base pairs is now that we know our proton donor is an acid and a proton acceptor is a base. If you give a proton acceptor a proton, what is it now? It's a proton donor. So it's easier than that. I'm a proton donor. Right? And he's a base, he's a proton acceptor. Who's the proton donor now? right? He's got an extra proton. And you get that. Now you're a bass.
Nothing.
Oh, now you're an acid.
Oh.
And that's all next day is we write down back and forth.
I need to. Do we need to know how to draw like the Lewis diagrams in this?
If you knew how to write those ones, literally those three, that probably would be helpful.
Okay.
You what? Oh, you were. Hold it. 1 second. I just realized everybody left. Doesn't this class end at 5 after?
Yep.
Can you boost our grade for staying?
That's a good idea.
Yeah.
Shows commitment.
You get quietly. Okay.
Let's go work it out.
You were musical, and I know how big of a commitment that was. What would work best for you? If I know you, could you write it next week and you want to get it out of the way? Because I don't want to. After musical sounds bad. However, if you're like right now with everything, that wouldn't be good. That's fine too. I just want to find a time that would work.
I can take it. It's not like the greatest important. I just think that I can't take it for because I have to be.
Oh, you have to physically be in
Yeah,
musical.
that's what I mean.
That's a
It's
good point.
not- I just have to be.
So a time next week.
Yeah, that is not.
When's your do you have a spare Isabella? No.
Okay.
You don't have a
Wait, I
lighter
need to
block of
find
any kind.
No.
You're not one of those
It's this one. It's this one.
instruments.